Hello everyone. We are entering to the new chapter Central Force Motion. Ninth chapter of the textbook. It is Central Force Motion. So you are all familiar with Central Force Motion, and what is a Central Force Motion or what is a central force? Central force on an object is a force that is directed towards or away from a point. So central force is always directed from a point or directed away or towards from a point. That's the basic thing about the central force. And what about the magnitude of central force? Magnitude only depends on the distance of the object from the center. Okay, so what are the examples, familiar examples of central force motion? Okay, first I will write the definition of central force. Central force is a central force on an object. Central force on an object is a force that is directed towards or away from a point, and the magnitude only depends on the distance of the object to the center. Center, or we can say that center of mass. Okay, and let us check some examples of central force. And the motion under central force is known as central force motion. And can you say some examples? Okay, you are all familiar with that. So the satellite motion and the motion of earth around the sun and electrostatic force are all examples of central force. And so let's consider the case sun and moon. Let us take this as sun and this is earth. E and S, sun and earth. And the mass of sun is taken as m and the mass of earth is taken as small m. And if the distance between the sun and the earth is taken as small r, the distance is measured from the center to center, left from center to center. So this is r from sun to earth. Let it be. Let us take the distance as r. So the earth is revolving around the sun, and this force, and why the earth is revolving around the sun? Due to the gravitational force of the sun. So what is the gravitational force of the sun towards earth? The gravitational force of sun towards earth is, let us take it as Fg. Definitely it is a vector quantity. It is minus gmm divided by r square. And what's its direction? It is in r cap, along r. And here we can see a negative sign, and what it does indicate? It indicates it is an attractive force. Negative sign indicates that it is an attractive force. Attractive force. That is, the sun attracts the earth towards the center of sun. It means sun attracts the earth towards the center of sun. Okay, so the negative sign indicates it's an attractive force. And what about electrostatic force? So this is an central force, and the force is acting towards this direction. That is, the sun is attracting the earth, so that due to the gravitational force sun, the earth is revolving around it. And we have another example. It is electrostatic force. And electrostatic force, and this is the force of interaction. Let us say force of interaction between two charges. Let it be P and it is Q. Let this Pu and Q are two charges separated by a distance r. Again, the distance is from center to center, and let it be Q1 and Q2. That's more comfortable to deal with. So what is the force, electrostatic force between these two charges? It is F is equal to force constant. It is the constant, you know that, 1 by 4 pi epsilon. It is Q1 Q2 divided by r square. Again, the direction is along r cap. So it will be positive if the interaction is repulsive, and it will be negative, the force will be negative when the interaction is attractive interaction or attractive force. Okay, so this force is acting towards a point. So Q1 attracts Q2. The direction is like this, and if Q2 is attracting Q1, it will be like this. So this is an example for central force motion. So here we are dealing with central force motions. So in this chapter we apply Newtonian mechanics or Newtonian physics to the general problem of central motion. Firstly, we will apply Newtonian physics to the general problem of central force motion, and we will see in this chapter some general features of a system of two particles interacting with a central force. So we will also see some general features of a system of two particles interacting with central force. And central force will be denoted F of r cap. So we will also see, after making a simple change of the coordinates, we shall show how to find a complete solution by using the conservation laws of angular momentum and energy. You already studied about the conservation laws of angular momentum. So by using the laws of conservation of angular momentum, we will uh, find the solution of central force F of r. So, and also we will see, we shall apply these results to the case of planetary motion. F of r is proportional to 1 by r square. We will also discuss the planetary motions, and in that case F of r, the central force is proportional to 1 by r square, or F of r is inversely proportional to square of the distance between the points, r square. Okay. Also, we show how the predict Kepler's empirical laws. Also, we will discuss about Kepler's laws. So, for the first session, here we have to study the central force motion as a one body problem. So, here we will discuss one body problem, taking as central force as one body problem. So the section 9.2 in the textbook. Central force motion. Central force motion S is one body problem. One body problem. So here we are considering an isolated system consisting of two particles interacting under a central force F of r. The situation is, here we are considering an isolated system. There is no external forces acting on that system. That's why it's called isolated system. So, isolated system of two particles. Let us represent the two particles in a coordinate system. Here we are considering two particles. First particle of mass m1 and the second particle of mass m2. And the position vector to m1 is taken as r1, and the position vector from the origin, or position vector of m2 is taken as r2, and these two particles are interacting under a central force F of r. These two particles are interacting under a central force. Under a central force F of r. The particles of masses m1 and m2 with position vectors r1 and r2 respectively. So what is this distance? This is r1 and r2, and what about this distance from m2 to m1? Let us take this r, and what is the expression for r? R is equal to r1 minus r2, And what is r? The magnitude of the vector r is equal to magnitude of r1 minus r2. And here we can write the equations of motion of m1 and m2 separately, and the force of interaction is only the central force. There is no external forces acting on these two particles. It is under central force. Okay. So here we are seeing two particles. And how can we convert this situation to a single body or a one body problem? Yes, by taking center of mass. So we will see that. So we can first we can write the equations of motion. We can write the equation for motion. Equation of motion. Equations of motion. For m1, m1, the position vector is r1. Therefore, m1 r1 double dot is equal to, what is that? F of r into r cap. And what is r cap? This is r. And what is the direction of r cap? This is the direction of r cap. So this is the equation of motion for m1. m1 into the acceleration will be r1 double dot. The position vector is r1, therefore the velocity will be r dot, and r double dot will be the acceleration. It is equal to f of r into r cap. And also we know that there is no external forces acting on that. It is only it is under central force. So m1 r1 double dot is equal to f of r r cap. And what is it is for m2 is m2 r2 double dot is equal to minus f of r r cap. Okay. So force is attractive for f of r is less than force is, okay, we can write here, force is attractive f of r or force is attractive if f of r is less than 0, negative, and force is repulsive if f of r is greater than 0, is positive. If f of r is positive, the force is repulsive. So these two particles are interacting each other. So if this mass is interacting to this mass or this particle m1, if the interacting force is taken as positive and the other forces can be taken as same force with a negative sign, that is happened here. So we can couple the equation. Let us take this is equation number 1 and this is equation number 2, so that we can couple these two equations together by r. So we know that, let's take another pen. We know that r is equal to, r is equal to r1 minus r2, and also the center of mass vector. Here we are coupling these two equations, equation 1 and 2. We are going to couple these equations using this r. And for that, here we are considering two particles. and we can construct a center of mass vector that all you studied earlier. So if R vector is the center of mass vector, this is the center of mass vector. R is equal to m1 r1 plus m2 r2 divided by m1 plus m2. So there is no external force is acting on the masses m1 and m2, therefore R is a constant. Yes. So this is the center of mass vector R, and there is no external force acting on m1 and m2, so the position of m1 m2 is a constant, so that the vector R will also be a constant. So we can write the equation of motion for R, vector R. This is the center of mass vector, and if we are denoting in a figure, this is our coordinate system, this is the mass particle m1, this is the particle of mass m2, and this is the vector connecting m1 and m2. This is the vector connecting m1 and m2, which is R, and if this m1, this is m2, and this is m1, this is m1, this is m2, where is the position of the center of mass? It will be lies in this line in accordance with the mass of m1 and m2. If m2 is greater than m1, the position will be towards m1 or near m2, and if m1 is greater than m2, the position of this center of mass will be near m1. So this is the center of mass vector R. Okay, and the expression for center of mass vector is m1 r1 plus m2 r2 divided by m1 plus m2. Okay, we can also write the equation of motion for R, and equation of motion for R is trivial. The equation for small r turns out to be like equation of motion of a single particle, and the solution is, okay, so we can write the equation of motion for R. It will be R double dot is equal to 0. Okay, or m R double dot is equal to 0. Okay, so the equation of motion will be R double dot is equal to 0, or m R double dot is equal to 0. And the equation, or when we integrate this equation, integrating we will get R is equal to Vt plus C. You take the integration d square r by dt square is equal to 0 from this equation, and once you integrate, you will get r dot is equal to some constant. R dot is equal to some constant, let it be V, and you again integrate R dot, you will get just Vt plus the constant of integration is C, and let us take R is equal to R0 plus Vt. here this constant is taken as r0. Okay, r0 and v depend on the choice of coordinate system. r0 and v depend on the choice of coordinate system. The values of r0 and v depend on which coordinate system that we are choosing, and the initial condition, if the value of r initially it is r0, then r is equal to r0 plus vt. And to find the equation of motion for r, we have to find the equation of motion for r, small r. And divide equation 1 by m1 and divide equation 2 by m2, 1 by m1 and 2 by m2 to find, this is for to find the equation of motion for r, equation of motion for r. So 1 by m1 is equal to r1 double dot is equal to f of r cap divided by m1, and 2 by m2 will give you r double dot is equal to f of r minus f of r cap divided by m2. And put this is equation number 3 and 4. This is 3 and this is 4, and if you subtract 4 from 3, you will get r1 double dot minus r2 double dot is equal to 1 by m1 plus 1 by m2 f of r cap. You just check this, and you can rearrange and expand all this. m1 m2 divided by m1 plus m2 into r1 double dot minus r2 double dot is equal to f of r cap. And what is this m1 m2 divided by m1 plus m2? It is nothing but the reduced mass mu. Reduced mass. So the equation have become mu r double dot is equal to f of r cap. What is this? This will be r double dot, since r is equal to r1 minus r2. Okay. So mu r double dot is equal to f of r cap. And looking to this equation, okay, the last equation, looking to this equation, you feel that this is an equation for a one body problem. So the two body problem is reduced to one body problem, since we are using the idea of center of mass. So the equation is reduced to a one body problem. And so this is the here f of r will be different for different situations. So what is r1 and r2? The equation is identical to the equation of motion for this equation is identical to the equation of motion for a particle of mass mu acted on by a force f of r into r cap. So there is no trace of the two particle problem remains. So the problem is reduced to one body problem. That's it. The two particle problem has been transformed to a one particle problem. Okay. So the problem now is to find r as a function of time. So here we have to find the r, have to find the vector r. So for that, once we know r, we can easily find r1 and r2 by using the relation. So by solving this problem, you will get this r, and from r you can find what is r1 and r2. So that, and the next we will find how to find r1 and r2. Once you find r1 and r2, you can find the motion of m1 and m2 respectively. So we can write r1. We have seen that r is equal to r1 minus r2. From the figure you can write r is equal to r1 minus r2, and we find that r is equal to m1 r1 plus m2 r2 divided by m1 plus m2. And solving for r1 and r2, this is a homework for you. Solving for r1 and r2, put r1 is equal to r minus r2 and substitute in this equation. You can find the value of r2, and if you put r2 is equal to r minus r1, you can find the value of r1, and by solving that way you will get r1 is equal to r plus m2 divided by m1 plus m2 into r, and r2 is equal to r plus r minus m1 divided by m1 plus m2 into r, and m2 here m2r, this is r, m2r divided by m1 plus m2 and here m1r divided by m1 plus m2. These are the position vectors of m1 and m2 relative to the center of mass. Relative to the center of mass. And you can see the figure here. From the center of mass, the position vector to m2 is minus m1r. So here it is minus. Here it is minus m1r by m1 plus m2, and the position vector from the center of mass to the mass m1 is m2 divided by m1 plus m2 into r. You can find by using or by looking to this geometry of this figure. Here you have r1, r and r2, and you can find the distance is r minus r1 and r minus r2, and you find the value of r1 and r2 from this equation. Okay, so we find the position vectors of M1 and M2 relative to the center of mass. So here we got an equation for the center of mass, and the force is reduced to one body problem. So here we have to find the solution of the center of mass. Uh, so it will depend on the situation that we are considering. It will be different for different situations, and f of r r cap depends on the particular form of f of r. F of r ne depend ചെയ്തിരിക്കും. So however, a number of properties of center of force motion hold true in general regardless of the form f of r. Okay, so um, there are a number of properties of central force motion hold true in general. So there are some general properties of central force, uh, even if the form of the central force is different for different situations. There are some basic or some general properties of central force. We will discuss that in the next session. Okay, thank you. Here we are winding up here.